And I'm going to talk to you, it's partly a follow-up to what you heard from Tracy this morning. And it's really about assessing citizen science data. So this is a statistical analysis of some of the Roadwatch data that you heard about this morning. And the title is, Can We Trust Their Data? And it's about evaluating this particular data set to monitor wildlife along a highway. And this is really the issue. Here's a quote, and you could pull this quote from a lot of places that deal with citizen science data. This one happens to be from a recent paper, a really good paper. I strongly recommend this, and I'll circle back to it at the end. But I'm just going to read this quote. And it's, while the conversation that was being talked about here was about Christmas bird count data, while the conversation initiated for the most part by Cornell University ornithologists, seems to have popularized citizen science so that it is being taken more seriously within the scientific enterprise, the vast majority of scientists still consider volunteer-generated data to be much less rigorous and the margin of error significantly higher than that collected by professional scientists. And we could argue about whether it's really the majority of scientists, but there's still a lot of concern in the literature around the quality of data collected by non-professional scientists. The published literature around this, where people have actually tried to do assessments, is varied. It's mainly focused on the accuracy of data comparing experts and volunteers. So usually these are in situations where a scientist is using volunteers directly, they're training them, and then they're comparing two data sets. Some studies have reported a greater degree of data variability, and there's some good work on marine ecology, forest measurements, and water quality. And a lot of studies have reported high reliability of citizen monitoring data. High school students collecting water quality data, coral reef fish surveys, stream measurements, and bird counts. And I purposely listed the same kinds of studies between the two of them, between those two cases in the literature. So in some cases, the data are showing up to be strongly reliable. In other cases, there's some questions. Most of that literature focuses on really systematic data collection. And again, this is usually scientists who have programs in place and pull citizens into those projects, train them, and compare data. And what we wanted to look at is something a little more unsystematic, where there is some volunteer training, and we heard about that with Roadwatch this morning, but it really lets the citizens loose, if you want, to go out and collect data. So the purpose of this work was to evaluate the quality of this Roadwatch data. It's, again, just a reminder, this is in Crow's Nest Pass, and it's aimed at monitoring wildlife crossing and wildlife along the highway. And it's work that was done by a graduate student from the University of Montana, Kylie Paul. And we've recently published a paper on this, and I'll give you the reference for it at the end if you just can't get enough out of the talk here today. So just a reminder, this is the part of the world we're looking at, and whenever I point to a slide, I'm going to do it over there because that's where I can see. So this is a 46-kilometer stretch of highway. We're down in southwestern Alberta for those of you that are visiting us here, and this runs out from the grasslands into the foothills. The gap here between the mountains and foothills is very, very narrow. It's one of the shortest transitions actually anywhere along the Rocky Mountain front. It literally goes from grasslands right here to mountaintops right when you get up into the pass. And the study goes to the BC border. There's nothing magical about that border from a scientific standpoint, but it's a jurisdictional boundary, and the highway rules and highway size even changes a little bit. I love this image. This shows you the Rocky Mountains in that part of the world looking south. And so this is the Frank slide showing up right here. This is the highway through the Crow's Nest Pass. And the stretch of highway that was being monitored was, I must have had too much coffee this morning, was from just out here on the plains in through the pass, and the Continental Divide is right here. This is the Alberta-BC border, and the Montana-Alberta border is just right around here. So for those of you that know this part of the world, this is the Flathead Valley here that there's so much discussion about right now in terms of park expansion. This is the BC side of the Flathead Valley, highest concentration of grizzly bears and wolves in south of Alaska and mainland North America. So incredibly rich area. And you can see the importance of this Crow's Nest Pass area as a gap through the mountains. It's pretty much an unbroken chain here, and then north of Highway 3 as well, along the Continental Divide. And then there's this large gap through here where the communities sit. There's another gap down here, and it's very creatively called the Gap. This is where the Livingston Old Man River flows out through the gap, and it's another break in the chain, but it doesn't go all the way through the Continental Divide. So the bottom line is it's a really important area ecologically for both north-south and east-west animal movement. For these guys. And the difference in issues that all of these individual species create mean different kinds of management challenges as well as different kinds of potential data collection issues. Grizzly bears, we know, and Tracy probably mentioned this morning, that we know this area is already fractured for grizzly bears. There's a genetic break between the sides of the highway, but grizzly bears still cross the road. And 2, 3, 4 grizzly bears crossing that highway in the course of the year is incredibly ecologically significant. That's significant gene flow. We need to see that movement. Bighorn sheep use the area primarily as summer habitat. There are some winter habitat areas as well. And the sheep stay very close to the road, or the road goes through some very high quality sheep habitat. And it creates conditions where there's a possibility of highway collision, and Tracy no doubt covered that this morning. It's an important area for moose, especially about right in the middle of that area. There's some critical wetlands, and again, from a highway vehicle collision standpoint, it's a pretty significant issue if somebody hits a moose, both for the moose and the person in the vehicle. And then much more on the less rare side, mule deer and white-tailed deer both cross this highway and use the margin of the highway extensively. So what did we do, or what did Kylie do here? From June to August in 2006, a few years ago now, she drove up and down Highway 3 4 times a day, 5 days a week. She did it, this is the wonderful thing about having graduate students. So 20 drives a week, and what she did was break those drives up so that they were 6 hours apart, and then each day she shifted those hours 1 hour. So that over the course of that whole period of time, she's sampling each hour of the day equally and night. So she's driving this stretch of road day and night, creating a systematic sample. And that allows us to compare a systematically, scientifically, if you want, collected sample to be compared to what Roadwatch volunteers were doing. Kylie needed to go back to school in the fall, and so from August to May, so August 2006 to May 2007, this was driven about once a day, 5 days a week, partly by people that were in the room here. There's a minimum of 1.5 hours between drives, usually more than that when Kylie was doing them, but we wanted to try to make sure we weren't counting the same animals twice. All live animals seen within 100 meters of the road were recorded. And in Roadwatch data, if you remember from this morning, any animal that's seen from the road can be counted, and I'll come back to that a little bit. Altogether, between Kylie and folks in the past, this was 432 trips up and down this road and just a little under 20,000 kilometers of systematic sampling. During that time, there was 573 individual wildlife sightings, so wildlife was seen on 260 out of the 432 drives. So that constitutes the systematic sampling, the scientific sample piece. Now, the Roadwatch data, which you already know a fair amount about, was collected during that same period of time, and we just clipped out that chunk of data so that we were looking at the Roadwatch data that was collected over those same months. Statistically, one of the issues with doing validation of these kinds of data, and with a lot of citizen science programs, is that not all of the areas being sampled equally. So Roadwatch works with people who are driving the highway at different lengths of the highway at different times of day. They aren't always driving the whole stretch. And they're not, they're driving probably mostly in the day or during shifts going to work, and not all the sampling is equally spread over space or time. And the other issue for any of you that are statisticians in the room is that there's no negative data collected. So what we don't know is when people are not seeing animals. And statistically, if you're trying to work out exactly what's happening out there, you need to know when you're not seeing things as much as when you are seeing things. And then the sample during this period of time, there were 24 individual road watch participants that contributed 640 sightings of wildlife within 100 meters of the road. They also spotted wildlife that was further away from that, but we didn't use it. So those are the two data sets. We did 5 different things with those data sets. First of all, we checked to see if there were differences in the reporting frequency. So did the systematic data show a different relative frequency of the animals? And what we're trying to get at here is there bias in citizen science reporting? Are people likely to record rare things more than common things? 2, we wanted to assess whether there was spatial clustering. So are those wildlife sightings equally spaced along that whole set of highway in both data sets, or are there some clusters? And if there are clusters, then it becomes interesting for highway mitigation. We then assessed the spatial similarity between the two data sets. So we broke the highway into 1 kilometer chunks, and we compared what Kylie saw to what road watch participants saw. And then we did that without 1 kilometer breaks. We said, okay, if you just looked at the highway, and the reason why we chose 1 kilometer is we had done some analysis around 1 kilometer chunks previously because it seemed like a good spatial resolution based on the data we had. And then we said, okay, what if you ignore that 1 kilometer break? What is the space, what is the geographical space where those two data sets correspond? And then finally, if the two data sets are similar, if it shows that road watch participants are doing a good job of collecting data, what's the minimum number of data points that you need, so the minimum number of volunteer data points, where you can feel relatively comfortable with the quality of the data set? So here's what we found. There's 2 columns here. Systematic and opportunistic. You can see that by far the highest number of critters seen were deer, 504 on the systematic and 516 with the opportunistic data, so really, really similar. But then there's some differences. Road watch participants reported a higher proportion of bighorn sheep, of coyotes, and moose than did the systematic sample. And the systematic sample, there was slight statistical significance here, but the systematic sample reported a slightly greater frequency of elk. So the bottom line here is we did see some bias in reporting. What's important to talk about later is how much does that matter and what's the purpose of the work. So we'll come back to this. Without getting into the details of the stats here, there's a spatial statistic called Ripley's L, and this just allowed us to determine that yes, wildlife was clustered along the highway, and the systematic data came out a little bit different than the volunteer participant data, but pretty close. Clustering between 0 and 12 kilometers with the systematic data and 0 and 8 kilometers with the road watch volunteer data. Statistically not significant differences there. This is probably the most important result, and unfortunately the colors aren't showing up terrific on the slide here. But the dark bars are the systematic sample and the light bars are the road watch sample. And in a nutshell, what you can see here is that there's pretty good correspondence in space and in frequency between what road watch participants were seeing and what Kylie was seeing. And for me, this is kind of the bottom line graphic. There's an incredibly good correspondence between those two data sets. And the second most important thing is not only do we get this clustering, but if you do the detailed analysis on where the hot spots are, which is where these stars are on the bottom here, there's really good correspondence. So the take-home message from this is that the volunteer data set is showing exactly the same wildlife hotspots as a systematic data set. And then that last step where we looked at whether because that was the 1 kilometer chunks of road I just showed you, and if you do some analysis and you ask the question, well, is 1 kilometer the right spatial scale to look at to do that comparison? This basically says yes. Roughly between 1 and 4 kilometers, there's good correspondence between the two data sets. And this was partly done to validate earlier work that Tracy had worked on, and it showed that the 1 kilometer resolution was great. And then the final one is, when you do a whole bunch of Monte Carlo simulations, it shows that with 150 observations per year, at least within the context of Roadwatch, you can get a great sample of what's happening out there on the highway. And that's a much lower number than we expected going in. And I think it's because of the way people are covering that highway and how good a job they're doing at reporting these species. So it's a bit of an indicator of the quality of the observers as much as anything in that community. So a couple messages at the end of this. There is bias, and we've seen this in other citizen science programs as well, where people tend to like to report rarer things. And if you're driving a stretch of highway every day, you're less likely to report every mule deer you see, especially when you think about the numbers you just saw. In fact, if you're driving in the Crow's Nest Pass, it's pretty rare that you're not going to see a mule deer somewhere along that 46-kilometer stretch of road. And getting people to report that every day is tough. But it's one of the things that has been encouraged. And we've tried to have people over periods of time record the common things as well. But it depends on the purpose of your program. If you're catching enough of the common things, then and what you're really worried about is the hot spots along that highway, then you don't need to have every single one of them. And it is really important to get all of the rare ones, because they're rare. You know, you want to make sure that if a bear crosses the road in the Crow's Nest Pass, it's fantastic if somebody records that. If rare species are a concern, if you really want to try to get a handle on statistically how many animals are crossing the road, then what this shows is you need a long time just to get a big enough sample size to do that. The other thing that the data shows is that the temporal part of this is important. It would be nice to have more people recording information, for example, in this area at nighttime. You know, it's just, and if you think about it from an animal crossing standpoint, you're probably likely to get more animals crossing between dawn and dusk. You might have a higher risk of highway animal collision as well, both because of visibility and because of larger numbers. And then finally, negative data are statistically important. So it's a consideration in all citizen science work is figuring out a way that if it's an important part of the design, to capture when people are not seeing things. So the bottom line, I'm not going to read all this out. The answer is really yes. We can trust their data. It's a nice statistical comparison here, fairly elaborate design to get to that, to get to a fairly simple answer. But I think gives credit to both the design of the program and the quality of the people that have been collecting the data down there. And I just wanted to close with posing a couple other questions, I guess, here. And I didn't hear Dr. Blue's talk this morning, but I suspect she might have got into a little bit of this. And when I backed up to think about what's happening in the Crow's Nest Pass a little bit, part of me asked, well, is this really the right question to be asking? That is, can we trust their data? And this says a lot about science and positivism and what we're getting people to do. And I think we had a get-together here about a year ago on this same topic. And one of the things I raised is that, is citizen science really about having citizens become scientists or scientists become citizens? And I think it's a lot about doing both of those things. If it's just about citizens becoming scientists, that we're just reinforcing that scientism and positivism, and we're not letting the other kind of value and importance data be collected and considered as part of this. So thinking about citizen science programs, and this was, one of you raised this in the test on Tracy's presentation, but moving from purely teaching about collecting data towards engaging citizens in what's important to them and helping citizens talk to scientists about the kinds of questions that are being asked, how questions are being asked, what type of data are part of these programs. So I'll stop there. There's a reference to the details of the stats of this paper if you want to have a look, and I think we have time for a couple of questions.